that for a second. If it's a little bit like taking area under a curve where you use rectangles.
Okay.
You know how if I just had a regular curve and I would draw rectangles under it and I would sum up all the rectangles? That's the area under that curve.
Right.
But when you have a polar curve and you want the area between that line and that line, in other words, you want all this area in here.
Right.
The way you do it isn't with rectangles, it's with sectors. What is a sector? That's a sector. That's another sector. That's another sector. That's another sector. Well, the area of a sector is 1/2 r squared.
Okay.
So we're going to take all of these and sum them up. Whenever you sum them up, you get the integral of 1/2, whatever this polar function is. So it's going to be f of theta. We know it's theta because it's polar. D theta. And we're going to go from that radial line to this radial line. We're going to call it alpha to beta.
Okay.
And that's the answer for area under a polar curve. Okay?
Okay.
Now, it's a little bit tricky, but not that tricky. They give you the polar curve. What are my two radial lines? In other words, what's this line right here?
Like pi over 6.
What is it? It's 1.
Oh, yeah.
Theta equals 1.
Sorry.
So I'm going from this radial line to what? To theta equals what?
Well, to r equals 4 cosine theta.
The other radial line is the line that is tangent to that. What's that radial line?
Pi over 2.
Yeah. So this goes from 1 to pi over 2. What is the function? It's 4 cosine theta. So the formula is going from 1 to pi over 2 of 4 cosine theta, all of it squared, d theta. That's something you can plug into your calculator. I can plug it into Wolfram, and I get the answer.
And then we also have a 1/2 up front, correct?
Ah, yes. Which brings me to my next point. There is a quick and dirty method of calculating this, if you have to guess.
Okay.
And here's what it is. If you're making up this test, and you're putting 5 multiple choice answers on there, what are you going to put? You're going to put an answer, and you're also going to put half of the answer, right? Because a lot of people are going to put this in their calculator, and they're going to leave off the 1/2.
Okay.
So are there 2 answers on there that are separated by exactly double?
B and C.
Ah. And since the incorrect person's going to leave off the 1/2, what is the correct answer?
B.
Ah. without doing any work at all.
Here, can I plug in my calculator real quick and see?
Sure. Yeah, make sure you can get that because all of these require the calculator, pretty much.
Yeah, 1/2 math 9 0 2 1
This is
1 2.
it's a tricky one to plug in because you got to get all your parentheses right.
Yeah, so 1 to pi over 2 of 4 cosine theta all squared d theta 0.465.
There you go.
That was pretty cool actually.
Yeah.
I never thought about that.
If you're making the test, you're going to put two answers on there that one of them is going to include that 1/2 and the other one's not going to. Because
Right.
that's the most common mistake people are going to make is forget the 1/2, they're going to come up with this answer.
That makes sense.
If you're doing multiple choice, you're always going to put both of those answers on there. You're trying to trick people, right?
Right.
So it's not a bad technique. If you don't know how to do the problem, look for that 1/2. Once you find it, you know the correct answer has to be times the 1/2, not without the 1/2.
Right.
All right. Another area problem. Whenever you see shaded region problems, whether you're talking geometry or calculus, it's always a subtraction problem, right?
Right.
So it's the area of what? The circle
Yeah, R equals
minus what? The area of the what?
the clover leaf thing.
The rose petal.
Right.
Rose curve. That's the area of the shaded region.
Okay. So we just set up the integral the same as we did.
What's the area of the circle?
The area of the circle would be pi r squared.
We're in polar.
Yeah, that's true.
R equals 2 is that circle. So
Right.
the area of polar is 1/2 the integral of what? The function,
F of theta.
which is 2 squared d theta. What are my limits of integration? For that
Would they be 0 to 2 pi?
Yes. In other words, I have to go all the way around to get a circle with R equals 2.
Yeah, I have a question. So, like, if I have a problem where I'm doing area, but I don't have the picture of the graph, what would be a good way to know what I'm integrating?
It's tough. Even when you have the picture of the graph, it's tough.
Right.
That's the toughest thing about all of these, is figuring out your limits of integration.
Right, because most of the other stuff.
Okay, let's keep going. I think I can help.
Okay.
What's the area of the rose curve?
The area of the rose curve is 1/2 2 cosine 3 theta squared d theta.
What are your limits of integration?
Should be the same.
No, it actually isn't. The one thing to know about rose curves, which are one of the most common ones you're going to run into,
Okay.
it traces it out twice going from 0 to 2 pi. It traces it out once going from 0 to pi. So if I want that entire rose curve, I got to go from 0 to pi. If I go to 0 to 2 pi, I'm going to get two areas.
Okay.
And it's not easy to see. That's not a thing that's that easy to know, is that
Yes.
it traces
It's not
it
easy to
out from
visually see
0 to
that.
pi. Just know that that's the case with all rose curves.
Okay, so pi is twice, or 2 pi. It'll be twice the area that you want.
Yes.
So then it's going to be from 0 to pi most likely on a
Well,
rose.
0 to pi traces it out exactly once. Notice, let's look at this function. When theta is 0, what is the function value?
Theta is 0.
Uh-huh.
The function value would be cosine of 0 is 1. So 2.
Uh-huh. So this point right here, which is when theta is 0, is 2.
Okay.
Basically what happens is it starts there, you go like this, and by the time you reach pi, you've traced it out one time.
Okay.
And all rose curves are like that. You trace them out once going from 0 to pi. And there's probably a lot of other curves that are like that also. I don't happen to know what they are, but the main thing you're going to deal with is rose curves. So just remember that they get traced out twice when you go from 0 to 2 pi, as opposed to the r. The r has to go, r equals 2, has to go from 0 to 2 pi to complete a circle.
Right.
Okay. So this all goes, you can do the first part easy enough without a calculator. If you do the second part, you get, you want to go through this? It might be worth going through this.
Yeah. So integrate the first part.
Let's go through the first part. What's that equal?
Okay. So the integral of 2 squared would be increase power by 1, so 2.
No, just square 2.
Is 4.
What's the integral of 4? D theta.
4x.
4 theta.
Oh, 4 theta. Yeah.
And we still have that 1/2, so it's 1/2 4 theta evaluated between 0 and 2 pi. What's that?
Right. So basically 2 theta from 0 to 2 pi. So 0 and...
Start always with the top and then subtract out the bottom.
Okay, so then 4 pi and then 0.
Well, it's actually only 2 theta.
Right, so 2 pi times 2 is 4 pi.
Okay, so 4 pi is this right here. Now, the rest of it you need to do in your calculator.
Right.
Go ahead and do that. See what you get.
Okay, so...
And whether you include that 1/2 or not is kind of up to you. If you know how to put it into your calculator with that 1/2, then I would include it. Because the danger of leaving in the 1/2 off is that you will forget to do it at the end.
Right.
This is actually an integral that you can do without a calculator. In other words, the integral of cosine of 3 theta is sine of 3 theta divided by 3.
Right.
But we got to square it all. Go ahead and try that before I give you the answer.
So I put it in my calculator.
You should
and
get something like
9.42. So D.
Okay. I was trying to do it step by step, but this comes out to be pi.
Okay, it comes down to be pi.
So
then you get
4 pi minus pi is what?
Pi, so then 3 pi.
That's 3 pi right there.
Okay, that makes sense. Okay.
Okay. Oops, hold on. What is the slope of the tangent line to the polar curve at theta equals 0?
Well, so
Slope
we have to start with, well, dy dx equals dy d theta over dx d theta.
Perfect. In other words, what we're really looking for is dy dx, right?
Right.
Okay, and you're right. It's dy d theta over dx d theta.
So then
we have a
y equals r sine theta.
And it's a little tricky. It's not easy to figure out what dy d theta is it?
No.
Or dx d theta. So the only way we can do this is if we convert this polar function to xy coordinates.
Right.
Well, x is equal to r cosine of theta. Now y is equal to r sine of theta. Those are your basic identities.
Okay.
So what's x equal to?
So x would equal 1 plus 2 sine theta.
Well, go ahead. Yeah, no, you're right.
Cosine times cosine theta.
Yeah, exactly.
And then y would equal 1 plus 2 sine of theta, sine of theta, times sine of theta.
Yeah, so a critical step here is to convert it to parametric equations, because we start with a polar equation. And we're trying to figure out dy dx. We can't get to dy dx, even if we go dy d theta, unless we take this polar equation and convert it to two parametric equations.
So when we plug it into those x and y equations, that is turning it. We just turned it from polar to parametric when we did that, right?
Correct. And now notice that x and y are functions of theta.
Right.
Well, we're trying to figure out dy d theta and dx d theta.
So then we're taking derivatives separately.
Differentiate this. I got to differentiate that.
Okay.
And I can do it a number of ways. I can distribute it and then differentiate both terms, or the way I decided to do it was just use the product rule.
Okay.
We'll start with the numerator. Dy d theta equals what using the product rule?
So the 1 would go away.
Well, hold on. Let's write it out before you try to solve it in your head. I mean, you're really smart, and I know you can solve some of these in your head, but it's also a pathway to making mistakes.
Okay.
So let's just do dy d theta straight on as a product rule. Start with what?
Is product rule, is that one u times v equals u times v prime plus?
Yeah. Always start with the u. What's the u?
So the u is 1 plus 2 sine theta.
What is the dv?
dv. What's the dv?
Well, the v is sine theta, right? This was u. This is v.
And then we're taking v prime.
Yes.
So then just times cosine theta.
And then we got the rest of the product rule. What's the other end of it?
Then plus sine of theta.
Okay, yeah.
Times 2 cosine theta.
Uh-huh. So that's dy d theta.
Right.
All of that. Now, we're going to be asked to evaluate that at theta equals 0. So this is going to become a lot easier. When you plug in 0 for theta, a lot of these things wash out. Okay?
Right.
What is dx d theta?
Dx d theta would be 1 plus 2 sine of theta times negative sine of theta plus cosine theta times 2 cosine theta.
So here's our dy d theta. Here's our dx d theta. I'm going to write it up here at the top. I'm going to write the sine or the dy d theta first. 1 plus 2 sine theta times cosine theta plus sine theta times 2 cosine theta.
Yes. Yes.
I never have enough room. I'm dividing that by dx d theta.
Right.
Which is 1 plus 2 sine theta minus sine theta plus cosine theta times 2 cosine theta.
Right.
So there's our dy dx right there.
Okay.
We're evaluating it at theta equals 0. So now plug in theta equals 0. What do you get?
Theta equals 0. Sine of 0 is 0. So we get 1.
1 times
1
cosine of 0, which is
1
plus sine of 0. This whole term disappears, right?
Right.
Okay. We're dividing it by what?
Then we're dividing it by 1 times negative 1.
Hold on.
Plus
Sine of 0 is 0. This whole term goes away. When you multiply something by 0, the whole thing disappears.
Wait, sine of 0. I thought sine of 0 was. Oh, yeah.
Cosine of 0 is 1. Sine of 0 is 0.
Yes.
Okay, I still have a denominator. Cosine of theta, that's 1. But it's multiplied by the cosine of 0, which is 2. So I got a denominator of 2.
And then we get 1/2.
There you go.
Well, those problems definitely make a lot more sense now.
Well, good. This one's a toughie, because not only do you have to convert dy dx to dy d theta over dx d theta, but you got to change that equation into a parametric equation in x and y. Because there's no x and y. You can't figure out dy d theta until you have a parametric equation.
Okay. Do we have enough time to go over one more?
Yeah. If you don't, I'll make time. Is this the one you want to go over?
Yes, I'm confused by that graph.
All right. The only problem with this graph is figuring out the limits of integration, right? In other words,
right, and
we know that area is, and you can't quite use the same logic I did on the other one here, and I'll show you why.
Well, I did just realize that the multiple choice has all the same limits of integration.
Almost. No, you're right.
But I still don't know how. I don't know how it's 0 to pi. That's confusing to me. Anyway, so I would like to go over that.
What are we looking at? What kind of curve is that?
A snowman?
It's a rose petal.
Okay, it's a rose petal.
It only has 2 petals.
Okay.
In other words, instead of a typical rose petal, which would have 3 to 8, in other words, typical rose petals look like this. Well, this one only has 2 petals, but the principle is the same.
Okay.
You go from 0 to 2 pi, you trace it out twice. So to get this curve, you only have to go from 0 to pi. As with any petal. This is, go ahead.
So if the rose has, like, say, 4 petals, would you still
0 to pi?
Okay, so it doesn't matter the amount of petals. It's just 0 to pi will trace it once, and 0 to 2 pi will trace it twice.
Yes.
So that's just a good thing to know for petals.
Really good. Yeah.
Okay.
Because it's not that easy to figure out otherwise. I mean, you could go through a table. You could list a table of r's and thetas, and you could figure out that this thing gets traced out once when you go from 0 to pi.
Right. Is there a good way to recognize what equations will most likely turn out to be petals?
Yeah. I don't have a list in my book, but it's all about r equals, hold on a second. When you have equations like this, r equals a plus cosine theta, r equals a plus sine theta, those are rose curves. R equals a plus 3 cosine of 3 theta, that's a rose curve. This happens to be r equals sine theta times sine theta, which I would not have known was a rose curve if they hadn't drawn it.
Okay.
And I go on the assumption that all rose curves get traced out twice when you go from 0 to 2 pi.
Right.
So recognizing it as a rose curve you know that it's going to get traced out once by going from 0 to pi. So that's why everything goes from 0 to pi. They kind of give you a hint that that's the case. Okay. So what's the general formula for the area of a polar?
The general formula? R equals, for area, 1/2 alpha to beta of r squared d theta.
Yeah, or f of theta squared.
Right.
D theta. Because this tells you it's a function of theta, meaning it's usually a rose or a polar function.
Right.
So, if this is r, what is our answer?
C.
C?
Yes.
Yeah. There's got the 1/2. Sine squared theta squared is sine to the 4th of theta. Everything we need. Nothing else works. In fact, you can cross off the sine squareds of theta. So you know the answer has to be C, D, or E. And you can almost guess from that point.
Okay.
Because you know the formula is 1/2 the integral. Of course, that doesn't necessarily mean that this is the right answer, because, you know, you could have 4 sine theta or something like that inside. But you are looking for a 1/2 in front. And you're looking to go from 0 to pi. And that is exactly the function squared.
Right.
All right. Let's just, I don't mind doing this one. You want to do this one? I wrote on my paper, this looks like a trick question. Tell me what the general formula is here.
1/2 integral f of theta squared d theta.
Well, we know what the function is.
Right.
And we know what the radial lines are.
Wouldn't the radial lines be from 0 to pi?
Exactly. That's why I thought it was a trick question. It's too easy. So, you have your answer is 1/2 the integral from 0 to pi of that function 2 theta plus cosine theta squared. Now, the trickiest part of this is getting it into your computer or your calculator. I found it extremely difficult to put that into Wolfram Alpha. I eventually got it. And there's no shortcut here. In other words, you can't look for this half. You actually do find it right there, where one answer is half of the other. But you also find it over here.
And with the 4.9
right there. So that's not going to work here. But as long as you can get that into your calculator correct, it works. Now, I did discover something. I discovered that Desmos does not do these.
Interesting.
Yeah, I tried to do it on Desmos, and it says not able to do this one.
Huh.
But Wolfram Alpha does it. Now notice I did not stick the 1/2 in front. Merely because it's hard to put it in. Notice how you got to put it in to Wolfram Alpha. You got to say definite integral, parentheses, the function squared, and then you got to say it's a function of x and it goes from 0 to pi. So it's not that easy to put this in. I had to experiment quite a few times to try to figure out how to get that in. And of course I know it's correct because it tells me what I put in.
Right.
So I got 34.91, but I left off the 1/2 intentionally because I didn't want to screw up putting it in, trying to put in that 1/2. In other words, I guess I would put in a 0.5 in front of that definite integral. That's the easy way to do it. The other easy way to do it is to do it the way I did it and then just take half of that number.
Right. And I got 17.456 on my calculator.
That's what the answer is. In other words, this was easy because they told you what the one radial line was. It's not real easy to figure out what that radial line is there. But they tell you right there. So we know it goes from 0 to pi. The toughest thing about these polar questions, when they don't give you the radial lines, then you have to figure them out. And
they were nice on this one.
Yeah, to me, that is the toughest thing of all of these, is figuring out your radial lines. But
I would have to agree on that.
Yeah, they can be really tough. You know, I mean, if they give you a polar curve that looks like this, they say, what's the area? Well, you got to figure out what that radial line is. And you got to figure out what that radial line is. And there's ways to do it, but it's tougher for sure.
Right.
And then you could just multiply by 3 to get the total area of the rose petal. Or the easy way to do it would be to go from 0 to pi of whatever this function is.
Right.
Knowing that it's a rose curve and it gets traced out twice when you go from 0 to 2 pi. So if I want the area of this rose curve, I'm going to go from 0 to pi, put in the function, I'll have my answer.
Right.
John, feels like you're getting this stuff.
Yeah, I got an exam tomorrow on it, so
good.
I think I'm doing well on this stuff, and the sessions are definitely helping.
Good. Glad to hear it. It's helping me too. It's giving me a chance to refresh my skills on these areas that I don't get a chance to work with very often, and it's just as good for me as it is for you.
Right. I appreciate you working with me on it.
You're welcome. John, have a good evening. I'll talk to you next time.
You as well. Bye.